This is the screencast for section 2.3, example 1, polynomial functions of higher degree with modeling. So two specific polynomial functions that we will be dealing with in this section are cubic functions and quartic functions. Cubic functions are third degree polynomials. So in other words, there is a polynomial whose highest exponent has a degree of 3, and then an exponent of 3. Then the fourth degree polynomial is the quartic function whose highest exponent of x is 4. As a reminder to you, here are some terms for polynomials. First of all, a term of a polynomial is basically each section of the polynomial that is being added or subtracted to each other. Standard form of the polynomial means the highest exponent of x that term will go on the left and then will decrease from there. Then the constants are the numbers out in front of the x. The leading term is that x is the coefficient of the highest exponent of x term. So let's start example 1. Graphing transformations of monomial functions. Describe how to transform the graph of an appropriate monomial function f of x equals a sub n x to the n into the graph of the given function. Sketch the transform graph by hand and support your answer with a grapher. Then compute the location of the y-intercept as a check on the transformed graph. Holy moly! Okay, so let's start out with the first part. Describe how to transform the graph of an appropriate monomial function f of x equals a sub n x to the n into the graph of the given function. So our basic function here, f of x, is going to be x cubed. That was one of our basic functions from section 1.3. To get to g of x, the first transformation we performed was a horizontal shift left 1. Then that 4 outside is a vertical stretch by 4. That is a vertical change because it's outside of the quantity that's being cubed, and then it's a stretch because it's a number greater than 1. And we're multiplying, so it's a stretch versus a shift. So therefore, I know the basic y equals x cubed function looks something like, let's make that gray, something like this. So my new x cubed function is going to have a shift left 1 and a vertical stretch by 4 because it's going to look a little bit skinnier, and the x-intercept is going to move over 1. Maybe something like that. Now it's just a sketch, so it doesn't have to exactly look like it was stretched by 4. It is a sketch, and you told me what transformations are taking place, so just a sketch that looks, close to what it should look like is fine. So we did the sketch, we described how to transform. Now we're going to compute the location of the y-intercept as a check on the transformed graph. So y-intercept is where x equals 0. So f of 0, or excuse me, this would be g of 0, would be 4 times 0 plus 1 cubed. 0 plus 1 is 1. 1 cubed is still 1. 4 times 1 is 4. So this point right here should be 0, comma 4, which does make sense. Part B. The original f of x function or basic function that we are dealing with here actually isn't a basic function, but it is plain old x to the 4th, a quartic function with no other terms, quartic monomial function. So the transformations that took place here are a horizontal shift right 2, a vertical flip over the x-axis, and then a vertical shift up 5. So now if I graph, the original x to the 4th function looks like a parabola, except it's going to be a lot skinnier because x values that are raised to the 4th power are going to get bigger a lot faster than x squared would. So it's not a wide parabola like x squared. It's going to get higher faster. So now our graph of h of x is going to have a shift right 2, a vertical flip and then a vertical shift up 5. So 1, 2, 3, 4, 5. So I'm thinking somewhere down there it's going to cross the y-axis. But let's plug in 0 to the h function to see what our y-intercept is. Like I said, plug in 0. Negative 2 to the 4th. Negative 2 squared is 4. 4 times 4 is 16. That's a negative 16. And then plus 5, so negative 11, which makes sense. So this would be 0, comma, negative 11. The now try problem for example 1 is number 1. Describe how to transform the graph of the appropriate monomial function f of x equals x to the n. So first, let's call f of x in this case is going to be x cubed. There is a horizontal shift right 3, and then a vertical stretch by 2. So I described the transformations, sketched the transformed graph by hand, and support my answer with a grapher. Okay, so I will do that. So horizontal shift right 3 first. So the basic x cubed function, that is one of our basic functions, looks like that. Now we're going to shift it right 3 and make it tall and skinny because it got a vertical stretch. I don't know if that's right. It got a vertical stretch by 2. So I'm predicting that my y-intercept is going to be pretty negative here. I'm going to do that before I check everything with my calculator. That way I can check my y-intercept with my calculator too. G of x equals 2 times, let's see, we'll plug in 0 for x to find the y-intercept. Negative 3 cubed, yeah, there you go. That's negative 27 times 2 is negative 54. So this y-intercept down here is going to be 0, negative 54. So I've graphed the function in my calculator, but I do need to make sure, like I said, the y-intercept is going to be way down at negative 54. So I'm going to adjust my window so that, oh, I didn't hit zoom 6 here. So far so good, but now I want to see where my y-intercept is. I'm going to make my y-min at negative, if I want to see down to negative 54, I'm going to go with negative 75. And that does look like it crosses the x-axis at negative 54. Just to check, I'm going to hit trace, and I can see 0, 0, comma 54. So I was right.